Hello everyone, we are Cyberculture and this is our LCC 555 Cybersecurity 10 project. Our project focuses on three main areas: vulnerability assessment, command and control, and defense. Our environment included a Kali Linux attacker machine, a window target system, and a metapolice system for vulnerability scanning. We use tangible nexus essential for vulnerability assessment and POACH C2 as our command and control framework. Throughout the project, we collected screenshots and evidence to demonstrate both the attacker and defender perspective. Our presentation has this part. First, we will introduce our lab environment. Second, we will discuss our Nexus vulnerability scan results. Third, we will explain our post-C2 framework. Fourth, we will demonstrate the attacker scenario and remote code execution. Fifth, we will explain our defensive investigation, detection, and cleanup. Finally, we will summarize what we learned from this project. Our lab environment uses unique hostname containing our group name, Cyberculture, the system with Kali attacker, Cyberculture Kali, window 10 target, Cyberculture Winter, with a polytable target, Cyberculture Meta. Using unique hostname was important because it allowed us to clearly identify our system and provide reliable evidence in our screenshots. For vulnerability assessment, we installed Tangible Nexus extension on our Kali Linux system. The purpose was to identify vulnerability on our metapolitable target. After confirming Nexus was running correctly, we performed a vulnerability scan and analyzed the result from a defender perspective. The Nexus can identify many security issues. The results show 20 critical vulnerabilities, 28 high vulnerabilities, and 33 medium vulnerabilities. Because security team cannot fit everything immediately, we prioritize vulnerabilities based on severity and potential impact. The most important finding involved was Surface CDN vulnerability as an MP and Apache Tomcat issue. One major finding was related to Apache Tomcat vulnerabilities. Nexus identified possible remote code execution risks involving Tomcat components. Remote code execution is highly dangerous because it can allow attackers to execute commands directly on the system. Another critical issue was that installed Tomcat function was unalive when the CVS score of 10. Our recommendation was to upgrade to a supported function and remove unnecessary export service. Our remediation strategy focused on reducing risk. For Tomcat, we recommend upgrading to a supported function with strengthened management interface, disabling unnecessary service such as AJP. For other findings, we recommend removing default application, fixing CTN configuration, and migrating a supported operating system. For the attacker portion, we selected post C2 as our command and control framework. We selected from the C2 matrix because the project required us to use a different framework from Slaver. Our goal was to demonstrate the complete attack life cycle: initial execution, command and control communication, remote code execution, detection, and cleanup.
Remediation. Our remediation strategy focuses on reducing the highest risk first. For Tomcat vulnerability, we recommend upgrading to a supported version, disabling unnecessary services, restricting management interface. We also recommend removing unnecessary web application and migrating unsupported operating system. Framework POACH C2. For the attacker phase, we selected POACH C2 as our command and control framework. We selected this tool from the C2 matrix because the project required us to use a different framework from Silver. Our goal was to demonstrate the complete attack lifestyle, including exclusion, C2 communication, and remote code exclusion. For the attack preparation, during our control lab exercise, antivirus was disabled. This was allowed because antivirus bypass was outside the project scope. Our object was not to bypass security software, but to demonstrate how attack occur and how defender can detect them. For the remote code exclusion probe, proof this was one of the most important parts of our project. From our Kylie attacker system, we successfully received a push C2 implant callback from the Windows 10 target. The session shows username, student, hostname, CyberGP12, Windows 10. For the Windows 10, this proves that we achieved remote code exclusion and that the attacker system was communicating with the target. For the possible persistent indicator, after gaining access, we investigated possible persistent methods. We identified a possible registry rank key containing references to invite.docm and PowerShell. This demonstrated how attacker may attempt to maintain access after the initial compromise. For defenders, removing the implant alone is not enough. Persistent mechanism must also be removed. For the defender, Simon, after the attack phase, we move to the defender perspective. We deploy Simon on the Windows system to improve monitoring. Simon helped us collect information about process exclusion, network connection, registry changes. This provides evidence for incident investigation. For the incident response and cleanup, our incident response process included terminating malicious process, removing payload file, removing persistent entry, reviewing Simon load, re-enabling antivirus, performing additional scan. This allows us to return the system to a more secure condition. For the conclusion, this project allows us to experience cybersecurity from both attacker and defender perspective. As attacker, we perform vulnerability assessment, use a C2 framework, and a demonstrated remote code exclusion. As defender, we analyze vulnerability, investigated activity using Simon, remove persistent, and perform cleanup. The bigger lesson we learned is that cybersecurity requires both prevention and detection. Patching vulnerability reduces risk, while monitoring and incident response helps organization detect and recover from attack. Thank you for listening.